Well, let's go ahead and do another physics problem. A student jumps off a diving board 5 meters above the water's surface in a deep pool. The student's downward motion stops 2.1 meters below the surface of the water. Calculate the average deceleration. Now, I could have also said average acceleration. Remember, acceleration can mean speed up, slow down, or change direction. All right? So here it didn't matter. They just used the word deceleration. Calculate the average deceleration of the student while underwater. Because obviously, once the student hits the water, they begin to slow down, slow down, slow down, slow down, stop. And then obviously they come back up for air. All right, so you've actually got two different things going on here. And we gotta be careful about this. You can't just treat this as one big thing, one big action. You're gonna have to split it up. Maybe use two or more equations here. All right, let's go ahead and draw a diagram of this so we can see things a little bit more clearly. Here's the student, right there. They jump off the diving board and they begin to accelerate downward in the air. 9.81 meters per second squared. That's what you should be thinking. Remember, this is on Earth, right? On Earth. Here's the water, and you don't have to draw the water. I'm going to kind of just draw it there to help us see the difference between the two parts of this problem. Here's where the student actually hits the water, and then they slow down, slow down, slow down, slow down, stop. So the final velocity here is going to be 0. So let's go ahead and label some things here. First of all, let's go ahead and define our axes. Now, I want you to think about this, because this, again, sometimes confuses students, is they said the student jumps off the diving board. So I don't want you to think the student walks up to the end of the diving board and then jumps up in the air and then down into the water. All right? Yes, that's what that's what happens most of the time. But again, we're going to model this in the simplest way possible. So what we're actually going to do here is the student's going to walk up to the end of the diving board and then just take a step off the diving board. At that instant, after the student takes a step off the diving board, that's where our problem is going to begin. So when that happens, the student's initial vertical velocity is going to be 0. The student is then going to begin to accelerate, in this case, pick up velocity at a rate of 9.81 meters per second squared, because we're at the surface of the Earth. We don't know how fast that student actually hits the water. Don't know it. Weren't given that information. We don't know what his final velocity was just a split second before he strikes the water. But I do know whatever this final velocity was, once he hits the water, that's going to represent his initial velocity from here to here. Right? So again, we're breaking this up into two parts. This is part 1. And this is the final velocity just before that student hits the water. Part 2 now takes place in the water. And it turns out that that final velocity in the air, a split second before he hits the water, is going to be the same as the initial velocity, and it's not going to be 0. It's going to be the same as the initial velocity as he begins to slow down in the water. All right, so we could actually figure these things out. And it turns out we're actually going to do that. But just hold on. And then the student decelerates. So we're actually trying to figure this out. We don't know how fast the student decelerates or slows down in the water. So we're trying to figure that out. Let's see, do we have any other information? We do. It turns out that displacement from here to here is 5 meters. So I'm going to write it right here. You could also write it down here. All right, so from here to here is 5 meters. And we also know from here to here is going to be 2.1 meters. So there we go. I think we got everything now. So the initial velocity is 0, final velocity, and again, we can't just treat this as one big old problem. We're gonna have to break it up into 2 parts. So I actually wanna solve for this part here. So let's go ahead and try to solve this thing, all right? So I'm trying to find the acceleration. That means that I'm gonna focus on, and let me get another marker here. I'm gonna focus on this right here. I'm gonna focus on that part of the problem. See if I can solve that. All right? It turns out that none of my equations, I don't have enough information. Don't have enough information. The closest I can get is with this equation right here. Final velocity squared equals the initial velocity squared plus 2ax. I know the final velocity, 0. I don't know the initial velocity right here. I don't know that. Plus 2, the acceleration, I'm actually trying to figure that out. And then x is 2.1. These are all positive values because they're all in the downward direction. All right. Now acceleration, we'll talk about that a little bit. When I say these are all positive, I'm talking about the 2.1, I'm talking about the acceleration due to gravity, I'm talking about the 5. Those are all in the downward direction, so those are all positive values because I define downward as positive. Boy, if I could just find that initial velocity, then I could solve for acceleration. All right, well, let's try this. If I could find this final velocity, it's actually the same as this initial velocity, because those are just like an instant in time right there. So let's go ahead and do that. Now let's focus on this up here. So I'm going to circle this in purple, because I'm focusing in on that. I'm going to use the same equation. Velocity final squared equals velocity initial squared plus 2ax. The final velocity, that's what I'm actually looking for, equals the initial velocity, 0, plus 2, the acceleration due to gravity, 9.81 meters per second squared, and then this displacement is going to be 5. There we go. And again, we're looking for final velocity, so make sure that you square this side and you square that side. So what you're going to get is, let's see here, I got 9.9045. 9.9045 meters per second. So that's my unrounded off number. I don't want to round off there because that's not my final answer. So now I'm going to take that and I'm going to substitute it in. So 9.9045 meters per second. Don't forget to square it. So I'm going to take that number, I'm going to square it, and then I'm going to take it and I'm going to bring it to the other side of the equation. When I do, it becomes negative. It becomes negative. And then I'm going to divide that negative number by a positive 2, and I'm going to divide that negative number by a positive 2.1. And what I'm going to end up with is a negative acceleration. And I'll round off to, I want to round off to, I guess, 2 significant digits. So I'll round off to negative 23 meters per second. Right? If you're not using significant digits, then you could probably round off to negative 23.4. But I'm going to use significant digits here, so negative 23 meters per second. Now let's think about that. I made down positive. And you might be thinking, well, shouldn't the acceleration be positive here then? But think about that. Down is positive, and I've got a negative acceleration. So the acceleration is in the upward direction. Notice my velocity and my acceleration are in opposite directions. What does that mean? Object is slowing down. The object is slowing down, right? If this was positive and my velocity is still positive because it's still in the downward direction, that would mean that the object's speeding up, and that's not happening here. The student is slowing down as they move through the water, not speeding up. So again, our acceleration makes sense because the velocity is positive because it's in the downward direction, and our acceleration is negative because the acceleration is actually in the upward direction. And again, when both signs are opposite, our object is slowing down. Always try to make sense of your answer. All right, that's it for this problem.